Assalamu alaikum wa rahmatullahi wa barakatuh. This is Dr. Ali El-Moursy, and we are in lectures for Digital Logic Design DLD, lecture number 26.3 or part 3. In 26 part 2, we have learned how can we complete the design for the synchronous sequential circuit for the provided state diagram, which is for the serial 2's complementary. In part 1, we developed the state diagram. In part 2, we completed the design by driving the state table. Then using K-maps, we get the state equations. Okay, and finally, we can draw the whole circuit. So we solved the problem in full using D flip-flop. However, in the earlier lectures, lecture number 25, we have learned that there are other pieces, flip-flops, that we can use in developing synchronous sequential circuits. So for synchronous sequential circuits, we have 3 blocks that we learned. We learned the D flip-flop, the T flip-flop, and the JK flip-flop. In order to complete the loop, in order to give you a full comprehensive design steps, we need to demonstrate today in part 3 how can we change the design for using T flip-flop and JK. The design we are showing here is for the D flip-flop. So how the design will be different if the problem from the beginning asked me to use T flip-flop or JK flip-flop. It may be better for me to design using JK or design using T flip-flop. However, the easiest design is through the D flip-flop. Why? Because I have direct relationship between the state output and the D input. The equation for the state equations for the flip-flops are simply A of T plus 1 equals to dA, B of T plus 1 equals to dB, which is there. Okay, so all what we did here is we just copied the columns for A of T plus 1, B of T plus 1 into new columns for dA and dB, and we complete the design using the K-maps that as we demonstrated in the last lecture. Now, how the design will be different if I am using different type of flip-flop, the T and the JK. So today we will just move to the lecture 26 part 3, through which we design the synchronous sequential circuit example that we have here using T flip-flop and JK flip-flop. Okay. Now, first of all, we need to highlight what will be different if I am using different flip-flop. First of all, nothing changed from the state diagram. The state diagram is as it is. So no change in the state diagram. The state diagram describes the behavior of the circuits, the relationship between the inputs, the outputs, external inputs, external outputs, even the internal, the state output and the state outputs, and how many states do I have, and how to transition from one state to the other. So nothing is changing in the state diagram. Accordingly, the state table that we derive from the state diagram will remain the same. Agree? So accordingly, we need to scratch out anything not related to the difference between the design using JK and the design using D flip-flop. Okay, so we will just give ourselves a space here by just removing the state diagram. We don't need it anymore. State diagram has no change from what we have done before. The state equations will be different because I have different flip-flops. Okay, so we need also to develop new ones. Agree? So no need for the state diagram. The state table till the point that we discussed D is D. So nothing will change here. Okay, so we'll just remove the D parts. We also remove the state diagram, which is exactly the same. Not only that, the surprise is that if I'm using definitely also the input-output analysis, okay, the number of inputs, number of outputs for the circuit. Do you think that this will make any difference? There is no difference. So this part related to the input-output analysis will be the same. I have the same number of external inputs, the same number of external outputs, the same number of states. So I have the same number of state inputs and state outputs. Okay, so nothing here is changing. I will keep this as it is. Okay, no need for that. What else will be the same? Definitely here I wanted to remove those equations because the flip-flop that I am using is not the D anymore. So these equations do not represent that the change. Also, I wanted to remove the design for the D. I don't have D. Okay, there is no D input or intermediate input output from sequential between the sequential and the combination. Okay, so no need for this. Okay, I need to redevelop that for the JK and for the T if we go to the T. Agree? Now, what else? Okay, also here the state mapping. All of this we already done. No need. I only leave what I will need in order to complete the new design. There is a surprise here. Since the state diagram as is, the state table is as it is, okay, for the inputs and the outputs, do you expect that Y will be designed differently? The Y, the external output will be designed differently? No, there is no change, okay? Y is given through the TT and it has the exact same design. So its K-map, its equation will remain the same. Although I am using different flip-flop, okay? No need for any of this. I already have the design for Y. We derive the equation for Y and we get Y equals to B, the output of the flip-flop. The relationship between the A and A of T plus 1, B and B of T plus 1 is the same because this is related to the state diagram, which is related to the problem to be solved. The difference is that, so now all the circuit for combinational should be different. Also, I don't have something called DA. I don't have something called DB. Okay. And the type of flip-flops used is different. So right now, instead of having the D flip-flops, I want to use J, K flip-flops. Okay. So I will just remove the labeling here. And those flip-flops now will be replaced by the new flip-flop. So I'm going back to the beginning of the problem. So right now, I want to solve the problem using J, K, CC. JK flip-flop. Okay? Everything will remains the same. State table that we already developed will remains the same. But right now, we want to go back and replace those flip-flops by JK flip-flops. So we have actually two intermediate inputs between the combinational and sequential. We have, since those flip-flops are JK flip-flops, I have what we call the JA and KA. And I have here JB and KB. So still the inputs for the combinational are A, B, and X. But right now, the outputs of the combinational are Y, which is already designed. I want to design a new set of intermediate inputs for the sequential, outputs for the combinational. اسمهم J, A, K, A, J, B, and K, B. So what only differ between if I change the type of the flip-flop is the flip-flops themselves and the design for the combinational circuit for that. Designing the flip-flops indicates to me a new set of characteristic equations. Right now, I have A of t plus 1 equals to the equation for the JK. Equation for JK means JA A bar or K A bar A. This is the new characteristic equation for the first flip-flop. The second characteristic equation is B of t plus 1. B of t plus 1 equals to JB B bar or KB bar B. New two equations for the flip-flops. Those new two equations indicates that I have to design the combination circuit for the input, the outputs JA, KA, JB, KB differently. In the D flip-flop, the case is this was simple because A of t plus 1 equals to DA, B of t plus 1 equals to DB, and that's it. But right now I cannot do that. Actually, in order to design this circuit, I need 4 new columns in my TT. Those 4 new columns representing a new set of outputs or intermediate outputs. I need columns for 4 columns. Those 4 columns for JA, KA, JB, and KB. Those in-outs. New set of in-outs. From where can I get those? Okay. In D, it is simple because actually the equation representing that A of t plus 1 equals to DA, B of t plus 1 equals to DB. Here, the equation is complex. The equation is complex. Okay. How can I build a relationship? So I have something different from what I learned before. Actually, what I know about the JK is what we call the characteristic table for the JK. The characteristic table for the JK indicates that we know the characteristic table and the characteristic equation. The characteristic, so for JK, I have the following characteristic table. You still remember that? J, K, Q of T plus 1. By the way, we don't have only one Q of T plus 1 now. We have A of T plus 1, B of T plus 1. And we have JA, KA, JB, KB. Okay? So, characteristic table, we memorize it. We know it. The characteristic table tell me 0, 1, 0, 0, 0, 1, 1. And the characteristic table for the JK is Q, 0, 1, Q bar. This is the characteristic table. Now I am in a kind of awkward situation. Actually, I know from this table, I know A and A of T plus 1. And I want to drive JA and KA. This is upside down. The characteristic table show me how can I give what is input in order to produce the output. The relationship that I need is now between those two outputs, the Q and the Q of T plus 1. So I need a different table. This table is driven from the characteristic table, and it is called the excitation table. Excitation table. What is the excitation table? The excitation table is a table that shows Q and Q of T plus 1, similar to what I have here in my state table. Here I have A and A of T plus 1, B and B of T plus 1, and I want to drive JK. So this can be provided by another table called what? Called excitation table. The good news is that, the bad news is that you have to drive the excitation table from the characteristic table. The good news is that you don't have to do that because I will give you the table in the exam if you ever need it. It's a fixed table called what? Excitation table. Will be provided to you in the formula sheet in any of the exams. Okay? We are not asking you to remember 200 tables. It's good that you already memorize mean L characters. But now we want to demonstrate how can I develop the excitation table. I just want to show you how the excitation table could be driven, okay, and how it looks like. The excitation table has inputs Q and Q of T plus 1. And it should show me what is the corresponding value or columns for J and K for this case. So now it's kind of a flipped table. In the input side, it shows Q and the Q of T plus 1. And in the output side of the excitation table, I should drive meaning J and K. So it is the opposite of this. Okay? That's why it's called excitation. How can I excite the J and K to give me some combination of the Q and the Q of T plus 1? Right. This table is also should show me 4 different options. Okay? We will drive the table once here in this lecture, but later on you don't have to drive. It will be provided to you. So we need to see for all possible combinations between Q and Q of T plus 1, what should be the excitation or the inputs for the flip-flop. So we drive this from this. Now, let's go and check. I have here q and the q of t plus 1 both equals to zeros. Both equals to zeros. Agree? Now, how can I achieve this? What are the different inputs that I have to apply on J and K to have Q0 and the Q of T plus 1 0? Okay? I can view this as a similarity case. And then Q with Q of T plus 1 are similar. Where is the similarity in this table? The similarity in this table is provided in this row. So that means J with K, if they are both zeros, it will give me Q and the Q of T plus 1s are equal. And I can also see this as a setting or changing the value of Q to 0. So I need Q to be 0. How to get Q equals to 0? From the second case here. So both of those cases will give me what I'm looking for. Okay? In both of those cases, what should be the value of J? The value of J should be 0. Right. What should be the value of K? K could be 0 or could be 1. So that means I don't care about the value of K. So K is a don't care. Agree? Makes sense? Now, let's go and check the second case. Q0, Q of T plus 1 equals to 1. How can I get this combination? When Q0, Q of T plus 1 equals to 1, that means, okay, I can view this as setting Q of T plus 1 to 1, which is satisfied in the third column or in third row here. You see this? So this is setting the Q of T plus 1 to 1. Right, what else? Okay, Q0, Q of T plus 1, 1 means I'm flipping. That means if Q is 0, Q of T plus 1 should be 1. This also satisfies the condition. What is the values of J? J should be 1. What should be the value of K? K could be either 0 or 1. So that means I don't care about the value of K. If a K is represented as X. Okay? Make sense? Now, go to the next case. Q1, Q of T plus 1, 0. What satisfies this? This is a flipping because Q1, Q of T plus 1, 0 means that the last row here satisfies this condition. Right. Also, I can view this as setting the Q of T plus 1 as 0. Where this is satisfied, it is in the second row here. So both the second and the fourth rows will give me what I'm looking for in this. So in those two cases, J could be either 0 or 1. J is X, don't care. K in those two cases should be 1. Yeah, I drive the value. Lastly, 1 and 1. 1 and 1, you can view it as setting Q of T plus 1 to 1, which is satisfied here. Okay? 1 and 1 means both Q and the Q of T plus 1 are similar. So this is also satisfied up there. So the first and the third satisfy this option. In the first and the third, I have J either 0 or 1, which means J is a don't care. Right. Also, I can view, I can check the value of K. Value of K is 0 in both of those cases. That means definitely K here should be 0. This is what's called what? The excitation table. So we need an excitation table in order to design a synchronous sequential circuit using JK flop and as we will see also using T flip-flop. Okay. Now, after deriving the excitation table, we will use the excitation table to derive the JA, KA, JB, KB in our examples. This is all what I'm looking for. I'm looking for those columns. Without those columns, I cannot design the combinational circuit here. I cannot build my K-maps. Agree? So, accordingly, now I can drive JA and KA, given that I have A and A of T plus 1. So, A and A of T plus 1 zeros go to the excitation table. 0, 0, Q of T plus 1 is 0x. So, I have to use here 0x. Next, 0 with 0. Again, 0x. Again, next, 0 with 0 means I also have to use 0 and x. Then, here, 0 and 1. 0 and 1 means I have to go to 0 and 1 here. 0 and 1 here is 1 and x. So I have to use 1 and x. Next, so you know where I'm looking at? I'm looking at A and A of T plus 1. Which are representing Q and Q of T plus 1. And I'm driving for JA and K. In this row, I have 1 here and I have 0. 1 and 0 from the table here means X and 1. X, 1. Next, 1 and 1. 1 and 1 from the table here means X and 0. يبقى X 0. Last one here, A is a don't care. That means definitely both JA and KA should be don't cares. Agree? Make sense? Any question? Any doubts? Next, go to JB. JB and KB. Here I have to check mean. I have to check B will be of T plus 1. B and B of T plus 1 will allow me to get those two columns. Okay? B and B of T plus 1. 0, 0, 0, 0 means 0x. 0, 1, 0, 1 means 1x. 1, 1, 1 and 1 means x and 0 from the excitation table. 1 and 0, 1 and 0 means x and 1. 0 and 1, 0 and 1 means 1 and x. Next, 0 and 0, 0 and 0 means 0 x. Finally, I have x, 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 x. Now, I have succeeded to drive the full state table, the extension of the state table that will allow me to design the combinational circuit here that has 4 new outputs, JA, KA, JB, KB. Agree? Now, how can I solve them? Simply K-maps. Okay, so now I have to build 4 K-maps. K-maps. How many K-maps do I need? I need 4 K-maps for JA, KA, JB, KB, and each of those K-maps is 3 variables, A, B, X. Can we do it? Yes. Okay, so here let's start with JA. JA, the K-map looks like this. For JA, I have definitely here A bar A, B bar B, X bar, X bar. For JA, I have 0, 0, 0, 1, 0, 0, 0, 1. Watch for the screwing 0, 0, 0, 1, 0, 0, 0, 1, and then X, 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 X. Prime implicants, SOP or POS. So the contour that I can get here, if I'm using SOP, I can get this contour. Okay, so this contour is actually BX. Okay, can I take those together? Yes, but I will end up over non-essential because all of them are don't care. So I will exclude it at the end of the day. I'm looking only for the ones. This is essential, definitely. That means the equation for JA equals to BX. First equation. Next, KA. Okay, map. A bar A, B bar B, X bar X bar. KA X X X X X X X X 1 0 X X 1 0 X X. Again, I have only one here, so I can have the contour that actually the side contour, this side contour, which takes those together. Okay, so the term here is K equals to only one term. If you want to get it, this prime implicant is A bar, A cancelled, B bar, B cancelled. This is simply X bar. يبقى K equals to X bar, and this is definitely essential. Essential. By the way, this is chapter 3. Okay, so I don't have to do that. Okay, I'm just do that for the sake of completeness. Okay, but after you drive those, it's a problem from chapter 3. K-maps. You have the table. Now you forget the states, next states, okay, the state outputs, and you have a TT. You solve this TT for 4 variables. The second is K, KA, this is KB, and then JA and KA. We have now JB. JB, I have a K-map. A bar A, B bar B, X bar, X bar. For JB, I have 0, 1, XX, 0, 1, XX, 0, 1, XX, and 1, 0, XX, 1, 0, XX. This is a little bit tough because I have 2 ones that are, so I have to get at least 2 contours. So for this one, I cannot go to the left, I cannot go down, I can go only to the right. How far? I can only take those together. So the equation will be, this is definitely PIs. Even PIs here, prime implicants. The first PI here is, this contour is A bar X. The second contour is for this one. Now I'm done with this. With this one, cannot go up, cannot go right. I can go to the left. I will take this with this. which will give me the contour AX. Okay, both of them are essential. Essential. And A bar X, AX bar, this is simply X or JB equals to A X or X. A bar X, A X bar. So X or between them. Agree? Last one is KB. Last came up. XX01. طبعا A bar A, B bar B, X, X bar, X bar. So for KB, XX01, 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 XXXX, XXXX. Okay, so the contour here for this one, I cannot go to the right, I can go down and to the left. The contour is here. There are other contours for the don't cares, but I don't care about them. So the prime implicant or only one prime implicant اللي هو واخد اللي في النص ده, which is simply X, and definitely this is A essential. So the equation for KB is simply equals to X. So I get equation for JB, equation for KB, equation for JA and KA. Okay, I get my 4 equations. So now I have to do 2 things. I have to get the state equations. Don't forget. يبقى هنا, let me just put me in the state equations. يبقى state equations. We already get the equation for y equals to b. A of t. Hold a second. Now, يبقى component, this we have the state diagram. This is the state table, and here is the circuit. The third is the state equations. The first equation, which we didn't drive in this lecture, we drive it in the last lecture. Y equals simply to B. Okay, agree? Then I have A of t plus 1 equals to JA A bar. What's JA? JA is BX, then A bar, or with KA bar A. KA bar, KA is X bar. So KA bar means X. X ended with A. This is the first state equation. The second state equation is for TB. TB of t plus 1 equals to JB B bar, JB, which is the NX or between A and X, and B bar, or مع ال K bar B. K is X, means K bar is X bar. If I have here X bar B. Those are the 3 state equations. Those are 3 state equations. Okay, what's left for me? The implementation of the circuit. Okay, I already got the equations, and all what I have to do is to implement those here on the circuit here. Okay, so JA is BX. So I need to have, as Dr. Ali recommends for you, you don't have to connect the feedbacks to avoid the congested drawing. Just to avoid congested drawing. JA is BX. So I simply write here BX. Right, KA is X bar. I can simply write here X bar. That's it. Right. JB is the XOR between A and X. This is an XOR between A and X. A and X. KB is simply X. So KB here is just X. That's it. We are done. From the excitation table, we will be able to complete or have the outputs for the state table or intermediate input outputs. We drive, we get 4 K-maps, simplify using K-maps, get the equations, put the equations on the drawing, we get the circuit implemented. Okay, and here, so those are the state equations. This is the circuit, and here is the work. So don't worry about the excitation table. If I ask you ever to build the circuit using JK flip-flop, as you see here, designing using JK flip-flop is not easy. It needs one extra step involving the excitation table. That's why it's recommended not to go to the JK implementation unless the question asks you, or you know that the design will be better if you use JK flip-flop. Okay, T flip-flop has a similar scenario, but we will defer it right now. We will not. You can actually, let's do it. Homework. Design using T flip-flop. T flip-flop also needs the excitation table. It is in our textbook. You go and check the excitation table. We will mention how the excitation table for T flip-flop has been developed, and we will design one circuit using T, but not this example. So the homework for you is to repeat this design. We design the circuit using D flip-flop and JK flip-flop. Do it using T. Okay, this is all what I'm requiring from you as a homework, and see you inshallah in the lecture number 27. We will take more examples of how to build the state diagram. Okay, the flow of the work we already covered it, so we will not cover it again. We need to take more challenging problem for building the state diagram, which we will do it in lecture number 27. Thank you, and see you in the next lecture.